Welcome back. Let's continue with our lectures. Now we introduce air fault protection. Air fault protection is designed to protect medium voltage networks against ground faults. In air fault conditions, one phase is connected to the earth, either directly or through impedance. These faults are commonly in medium voltage systems. Air fault protection uses zero sequence quantities as measured values. The main measured quantities is zero sequence current and zero sequence voltage. To measure those, current transformers are connected in parallel across all three phases. The sum of three phases currents is measured. Under normal condition, the sum is zero. During an air fault, the sum becomes non-zero. The measurement quantities corresponds to 3 times of the zero sequence current. To measure zero sequence voltage transformers are connected so that the primary windings are connected in star. Secondary windings are connected in open delta. In normal operation, the open delta voltage is close to zero. During an L fault, a residual voltage appears. This residual voltage is zero sequence voltage. In overhead line networks, both zero sequence currents and the voltage measurement schemes are widely used. This figure illustrates a typical measurement scheme for zero sequence current and voltage. Phase conductors A, B, and C, current transformers for residual current measurements. Voltage transformers connected is open delta for residual voltage measurement. Air fault protection detects ground faults by evaluating those residual quantities. Now we'll discuss practical aspects of zero sequence current and voltage measurement. For reliable air fault protection, correct measurement setup is essential. First, current transformers. All current transformers used at one measuring point must be identical in all three phases. Their characteristic must match. In addition, phase load current should be similar magnitude. Large imbalance reduces measurement accuracy. For accurate zero sequence current measurements, CT ratio error must be small. Excessive CT error leads to false residual currents. Now voltage transformers. When measuring zero sequence voltage, ferroresonance is known risk. Ferroresonance can cause dangerous overvoltage in voltage transformers. To reduce this risk, an open delta damping resistor is connected to the secondary side. Typical values are resistance 20 to 30 ohms, power rating 300 to 800 watts. The resistor stabilizes the current and improves measurement reliability. In cable system, zero sequence current is measured using the common current transformer that surrounds all three phases conductors. This method is shown on the reference figure. Compared to overhead lines, cable networks allow much more sensitive zero sequence current measurement. Residual current below 0.5 amps can be detected. For this reason, sequence current protection is strongly recommended for cable networks. Zero sequence voltage measurement behaves differently. In overhead line networks, zero sequence voltage is easy to measure. In a cable network, zero sequence voltage can only be measured in cable termination, where the phase conductors are accessible. An important limitation must be noted. Air fault protection based only on zero sequence voltage is not selective. During the air fault, the zero sequence voltage appears almost uniformly across the entire galvanic connected network. This means zero sequence voltage indicates that the air fault exists. It does not indicate where the fault is located. Zero sequence voltage gives fault presence. Zero sequence current gives fault location. Understanding this distinction is critical for correct air fault protection design. Next, we explain how zero sequence voltage and current relays are used together in air fault protection. Zero sequence voltage relays are mainly used to detect the presence of an air fault. They indicate that the ground fault exists somewhere in the network. On their own, zero sequence voltage relays do not provide selectivity. They do not show which feeder or line is faulty. To achieve selectivity, zero sequence current relays are required. Zero sequence current relays determine the faulty line by measuring residual current. These relays can be non-directional and directional. With non-directional zero sequence current relays, a key requirement applies. The air fault current in the network must be clearly higher than the normal residual current. If this condition is met, the faulty line can be identified reliably. To improve protection reliability, zero-sequence voltage relay blocking is often used. The principle is simple. If the zero-sequence voltage relay has not operated, the presence of residual current alone is not considered sufficient proof of earth fault. In this case, the earth fault protection does not trip if the earth fault current is small. In this case, the earth fault protection does not trip. If the earth fault current is small, non-directional relay may not be sufficient. In such case, directional zero-sequence current relays are used. Directional relays determine the direction of earth fault current flow. The faulty line is identified because of the zero-sequence current direction is opposite to the healthy lines. This principle is illustrated on the diagram. The faulty line carries earth fault current toward the faulty location. Healthy lines carry capacitive currents in the opposite direction. Directional earth fault protection enables selectivity tripping even with low earth fault currents. Understanding the difference between voltage-based detection and the current-based selection is essential for correct earth fault protection design. Next, we will focus on earth fault protection in the isolated networks. In isolated neutral net systems, earth fault protection mainly relies on high sensitivity zero-sequence current protection. When required, directional zero-sequence current is also applied. When earth fault protection operates, the faulty line is disconnected. This causes a supply interruption for consumer connected on that line. In most cases, disconnection is followed by fast automatic reclosing. As a result, the voltage interruption usually does not exceed 0.2 to 0.4 seconds. Even short interruptions are not harmless. They disturb computer users, industrial processes, and automation systems. For this reason, reducing the number of earth faults is a key goal. Improving supply reliability starts with minimizing earth fault occurrences. This is especially important in the medium voltage networks. In the medium voltage system, earth fault occurs about 60 to 70% of all failures. Unlike face-to-face short circuits, single-phase earth faults often do not disturb low voltage consumer directly. However, they create earth fault voltages at fault location. The magnitude of earth fault voltage depends on earth fault current, ground resistance at the fault. Those voltages can be dangerous for people and animals near the fault line. Electrical safety regulation limit permissible earth, touch, and step voltages. In general, the maximum allowed value is 70 volts. If earth fault voltage exceeds this limit, the earth fault protection must disconnect the line immediately. This highlights the dual role of earth fault protection. Firstly, protect the power system and ensure reliability, and second, protect people, animals, and equipment from dangerous voltages. Next, we examine how earth fault current magnitude and direction affects protection operation. The magnitude of earth fault current depends on the total length of the galvanized connected lines. As a medium voltage network expands within the substation area, earth fault current increases. Earth fault current can be limited in several ways: by building additional supply substation, by dividing the network into smaller sections, by using arc substation coils. Limiting the earth fault currents reduces fault duration, voltage disturbance, and the extension of supply interruptions. Fast and selective earth fault protection further reduces fault clearing time, the number of disconnected consumers. Directional earth fault protection is a critical tool for modern medium voltage network. It enables fast fault clearing while minimizing unnecessary outages. Next, we explain when the non-directional earth fault protection can be used. Non-directional earth fault protection requires a sufficient large earth fault current. This current must be generated by a galvanically connected network, also called the background network. In this type of network, earth fault current follows through all connected feeders. As a result, each feeder contributes capacitive earth fault currents. Consider the situation shown in the previous diagram. When an earth fault occurs, the relay of line 3 carries the earth fault current generated by the rest of the network. For correct operation, the earth fault protection of line 3 must satisfy two conditions. First condition, the relay setting current must be higher than the capacitive earth fault current generated by line 3 itself. It ensures that normal capacitive current does not cause false tripping. Second condition, the relay setting current must be lower than the total earth fault current generated by the rest of the network. This ensures that the relay will operate when the real earth fault occurs. If both conditions are met, non-directional air fault protection operates correctly and selectivity. If the background network is small or air fault current is low, these conditions may not be fulfilled. In that case, non-directional protection becomes unreliable. This is the main reason why directional air fault protection is preferred in modern medium voltage networks. Now we look at the situation where non-directional air fault protection is no longer sufficient. If the required operation condition for non-directional air fault protection cannot be met, the directional air fault protection must be used. This situation typically occurs in isolated neutral networks with low air fault currents or complex networks configuration. The typical operation zones of directional air fault protection in the isolated network systems. Let us first look at the operating diagram which represents an analog relay. The relay operates only when all the following conditions are fulfilled. The zero sequence current exceeds the relay setting current. The zero sequence voltage exceeds the relay setting voltage. The phase angle between the zero sequence current and voltage vector lies within the operating sector, where the phi equals minus 90 degrees and delta phi is approximately plus minus 80 degrees. Only when the current follows in the correct direction toward the fault does the relay operate. Now consider operating diagram B, which represents microprocessor-based directional air fault relay. In this case, the relay evaluates reactive current rather than only magnitude of an angle. The relay operates when zero sequence voltage exceeds its setting value. Reactive zero sequence current exceeds the setting value. This digital method improves sensitivity and stability, especially for small air fault currents. In both relay types, the non-operation zones are clearly defined. Those zones are shown as shaded area in the diagram and prevent unwanted tripping during normal operation or external faults. Directional air fault protection ensures selectivity, tripping, and faulty feeders, reliable operation within low air fault currents, and stable behavior in the isolated and compensated neutral networks. Now we examine air fault protection in resonant grounded networks. In the resonant grounded system, the capacitive air fault current of the network is compensated by an inductive current. This inductive current provides an arc suppression coil connected to the transformer and neutral. In a fully compensated network, the air fault location is passed only by active component of the air fault current. The magnitude of this active current depends on the tuning of the arc suppression coil, the insulation condition of the network, the active resistance of the faulty location. As a result, air fault protection in resonant grounded network can be respond only to the active component of the air fault current. The reactive component of the zero sequence current is relatively small. The value depends on whether the network is undercompensated or overcompensated. Because the total air fault current is small, sensitive measurement is required. For this reason, zero sequence current is usually measured by the current transformers installed around the cable. This method provides higher sensitivity than phase CT. To improve the reliability of air fault protection in resonant grounded networks, zero sequence voltage relay blocking is commonly applied. The principle is as follows. If zero sequence voltage does not indicate the air fault, current-based protection is blocked. This prevents faults operated caused by transition of non-fault related currents. In modern systems, both short circuit protection and air fault protection are integrated into microprocessor-based feeder terminals. Those feeder terminals combine overcurrent protection, air fault protection, measurement, communication functions. As an example of modern microprocessor feeder terminals such as those manufactured by Siemens and Schneider, this concludes the section on the protection in the medium voltage power networks. You learned how protection system detects faults, limit damage, and maintain supply reliability. Thank you for watching and see you next time.